Our next speaker is Sergio Rincón Carvajal, if I'm not speaking wrong. And Sergio is a final year student of chemistry and biochemical engineering at Universidad de los Andes. And he joined the Professor Diego Gamba Sanchez team in 2021. And there he has been working on mechanochemistry applied to education. He's also a member of the Center for Research and Formation in Artificial Intelligence, directed by Professor Pablo Arbeláez. And there his research focuses on artificial intelligence applied to chemical and biochemical problems. So Sergio, the floor is yours.
So thank you very much for this presentation. And I'm going to share my screen. So please let me know if you are seeing my screen.
You can see it.
Okay. So first of all, thank you very much for this invitation. And thank you to Beyond Benign for the award. And the title of my work is Design of Simple Low-Cost Ball Mill for Teaching Mechanochemistry to Undergraduate Students. And this work was made together with my dad, Jesus Rincón Martinez, a friend of mine and of my dad, Alexander Tibocha, and the director of the Laboratory of Organic Synthesis and Bio and Organocatalysis, Diego Gamba Sanchez. So this presentation is going to be divided in 3 sections. First, a brief introduction into mechanochemistry and what were the objectives of this device. Then a design section. In this section, we are going to talk about how we designed the mill and what were like the characteristics to the design. And then the results sections. And in this section, I'm going to show you some reactions that we performed with the design device. So about the introduction, mechanochemistry has become an important research area. And this is because of 2 things. First, mechanochemistry allows us to obtain certain reactivities that are considered impossible. And these reactivities couldn't be obtained with its counterpart reactions with solvent. So usually mechanochemistry allows to discover new reactions that we usually can't do with reactions using solvents. And the most important thing for green chemistry is that mechanochemistry usually don't uses solvents, so the environmental impact of this field is lower compared to its counterpart reactions with solvent. Another important thing about mechanochemistry is that its applications are infinite. For example, if you search a little bit, you can find some reports in which these fields are applied to solar cells or pharmacotherapy. So its applications now are infinite. But when we talk about mechanochemistry, we usually think about chemical reactions that are produced by mechanical energy. However, now we can relate mechanochemistry to chemical reactions generated by grinding. Usually, when we think about mechanochemistry, we can think about a reaction that is carried out by grinding or by a grinding process. So, taking that into account, we can relate mechanochemistry and milling. And usually mechanochemistry could involve different types of milling. First, the milling that is made by specialized devices, and this kind of milling processes involves the use of some specialized device like ball mills, planetary mills, extrusion mills. In this case, the only difference between these devices is the way in which those devices apply the mechanical force to the reactants, but the principle behind is the same. And milling by hand. And milling by hand implies the use usually of mortar and pestle. So the first important thing to say here is that we usually use these devices in order to obtain reproducible results, because these devices allow us to control some variables of the reaction that guarantee that the results that we obtain are reproducible. However, when we employ mortar and pestle, we are not sure if we are going to have the same results, because every person uses different mixing or milling techniques. So maybe every person could obtain different results. Another important thing to notice here is this, and maybe you usually, when there is a reaction that is reported for mortar and pestle, a mechanochemistry reaction that is reported for mortar and pestle, you can extrapolate this reaction to you can carry out this reaction using a specialized device. However, the opposite is not true, because of the way in which these devices apply the mechanical force. Usually, you can't replicate the results that you obtained with an specialized device using a mortar and pestle, or you can't replicate the result milling by hand. So, taking that into account, there is an interest in these devices related to mechanochemistry. And in a mechanochemical process, usually we want to control different variables in order to obtain reproducible results. These variables could be related to the mill, for example, and usually the mill are allow us to control. The mill is can allow us to control the frequency of the process, the milling time, or the temperature in some cases. And maybe when you are using a ball mill, you want to control some variables related to the balls, like the mass of the balls, the number of balls, or the ball material. So we control these variables in order to guarantee reproducible results. And I think that the most important variables related to the mill that we want to control are the frequency and the milling time. These two variables are going to allow us to obtain reproducible results when carrying out a mechanochemistry process. Let's talk about a little bit about mechanochemistry costs. And here I can show you like some specialized devices that are used commonly for researching or for teaching in some cases. And if you can see here, the prices of these devices are between around $7,000 to $20,000. So these prices maybe could be affordable for institutions with high income, but for institutions with medium and low income, maybe these prices are not, or these devices are not so affordable. And for the reason, there is a problem related with mechanochemistry education. And the problem is that not all universities have the resources to teach students about mechanochemical work with specialized devices. So, the idea based on this problem was to design an affordable device that can introduce students to mechanochemistry. The idea was to design a device that illustrates how we work with the specialized devices and how we control the variables that I have told you in order to obtain reproducible results. So let's talk about the design. In order to control revolutions per minute and total milling time, we made a circuit and programmed the circuit with Arduino. So the idea here is that every module, here, like here, and here, allow us to control different things or include some functionality to the overall circuit. The main module here allows like the total control of all the total control of time and the total control of the other modules. Here, this module introduces the Bluetooth connection to the circuit. Here, this module introduces the speed control that allows us to control the speed of the motor that we are using in order to make the mechanochemical process. And here, this module allows to measure the revolutions per minute that the motor has at some specific time. So based on that, we obtain a circuit that could control a motor, and then we design an app in order to control the circuit. So this app was designed, it's a simple app, and you can use that to control the circuit. If you want, you can only connect the device by Bluetooth using your cell phone, and then you set the total time of milling and the revolutions per minute that you want. And yeah, with that, you start a mechanical process. If you want, maybe you can stop a non-finished process too. And let's talk about the mechanical design of the device. So we designed this reactor here, and this reactor is positioned on two rollers. So the rollers are connected to the motor and transmit the motion by friction. So the reactor is going to be rotating, and this rotation is going to be transmitted by the rollers. So here you can see a top view picture of the device. Here is the reactor, and here are the two rollers that are here and here in the picture. And another important thing to say here is that we designed a reactor that is a double reactor. So this reactor allows us to carry out two simultaneous reactions at the same time and with the same milling conditions. Um, and that is an important thing to say about this design. Um, about the results that we obtain with this device. First, I want to show you some videos that illustrate the functioning of the mill. Here you can see the reactor rotating on the two rollers, and here the circuit that is related to the movement of the reactor. So maybe you can see here and think something like, oh, this circuit is too complex. However, it's not too complex, and the idea is to publish this work uh, to publish this work in a journal and to publish too a guide in how to make this circuit without any knowledge about electronics or something like that. The code of the algorithmic part of the circuit is going to be publicly available. So the idea is that everyone without any electronic or programming skills could replicate this circuit. About the specifications of the device, the maximum milling time is unknown. However, we have used this device for more than 40 hours straight, and for the reason we can say that this device could be used for long periods of time. Another important thing is that the frequency range of the device is between 50 to 200 revolutions per minute. However, if someone wants more revolutions, uh, this person could change the motor. The circuit is designed in order to control motors that operates between 5 to 12 volts. So if you want to change the motor in order to obtain more revolutions, you only have to select a motor that operates between 5 to 12 volts. And the cost of the device, and the most important part, it's around $500. However, this cost was calculated taking into account that you don't make the mechanical part. But if someone wants to make the mechanical part and the electronic part too, this cost could be reduced. Let's talk about the reactions that we perform with the device. We synthesize oximes, um, and these molecules were reported and synthesized usually by hand. However, we extrapolate this reaction and carry out this reaction with a specialized device and with our device. And if you can see here in the table, uh, our yields are similar to those obtained with mortar and pestle and with a specialized mill. So our uh, mill is working well for this reaction. And another important example, and the last example that I have, is the synthesis of this molecule. And there is an important thing to say here, and it is that this molecule is difficult to synthesize by hand. Why? Because in this case, to obtain this yield, we were like grinding the reactants for like 7 hours straight. So it was terrible. So for the reason, it's better to use our milling. And if you can see here, we can obtain better yields using our milling. And these yields are something similar to those obtained by an specialized mill. So our mill works to synthesize this molecule better than its counterpart grinding by hand. So, about the conclusions of the work, the design device cost around $500 and generates yields similar to those obtained by a specialized device. And we plan to make future reactions and improvements to the device. We plan to synthesize more oximes and maybe to reduce the total material that we are using to make the device in order to reduce the costs. And we want to change maybe the motor in order to obtain more revolutions and high energy grinding. And maybe if you have some questions about the device or you are interested in my work, you can write me an email. I'm glad to receive some questions about this work. And if you want to see the original publication, here is my Twitter user. And there in this account, you can find like the original poster related to this work. So that's all. And thank you very much again for this invitation.
Hello, and thank you for your presentation. It was great. It was very cool to see you making something for much cheaper and just on your own with your team, which will definitely help a lot of more undergrad students to get to use some technology that is more like harder to obtain. So thank you for sharing that. So now we're just gonna move on according to our agenda. We're gonna go into breakout rooms. So there'll be one breakout room set up for Angie. If you have questions about her research or you want to talk to her, one for Sergio for his research, and then 2 other breakout rooms for the Beyond Benign team and the Green Chemistry Connections team. So feel free to join them. And again, introduce yourself, your name and your affiliation, and let everybody have a chance to talk in the discussion. So thank you.
Thanks. So, okay. So thank you so much, everyone. I hope you had a great discussion in the breakout rooms. And now I'm going to give some announcements and updates from the higher education team. Thank you so much, Gagan, for changing the slides for me. So first announcement is that next year we're going to be in a lot of different places. So if you are going to the ACS Spring in March in New Orleans, we're going to be there. We hope to see you in person. We're also going to be at the CSC in Winnipeg, the Canadian Conference. Also in the Biennial Conference on Chemical Education in August, and at the Green Chemistry Engineering Conference in Atlanta, Georgia. So if you are around this conference, we would love to see you in person and connect with you. Next slide. And this is also an invite for you to join our next Green Chemistry Connections event, which is going to happen in January 17th at the same time. And we're going to talk about green and sustainable chemistry education materials. We'll have some people from the ISC3 and also from the United Nations Environmental Program talking about their materials and giving you some resources so you can use in your class or even to learn about green and sustainable chemistry. And also, I'd like to thank all of our supporters for helping Beyond Benign to achieve what we plan to do and talk about green chemistry and give the students the skills they need to move towards a more sustainable future. And is that our next slide? And also thank our partners. But most importantly, I'd like to take this moment to thank you all, because this is the last connections of the season. So I'd like to thank all of our speakers for being here today, all of the award winners. Sergio, Angie, you're amazing. Gustavo, thank you so much. You're amazing too. Finally, I was able to talk to you. All of our participants, Cynthia, Gagan, Jess, Sarah, Natalie, Nim, for all of your work. Oya Shalapi, sorry you're not on camera, so I missed you. Oya Shalapi, for all of your hard work. And I just wanted to say thank you and happy holidays. And I think Nim wants to say something from the higher ed team too. So I just wanted to say thank you.
Yes, I just wanted to join in and say thank you so much. And that a big congratulations to all of you as award winners. Your presentations were fantastic. Juliana said it better than I could, but I just wanted to say how impressed I was and how amazing this is to have you all as part of the community.
So yeah, thank you so much. And I hope to see you in January. If you have any questions, if you want anything at all, you know where we are. So thank you.